All right, today's our first video for real analysis. And we're going to start talking about sequences. We're going to do a reinvention exercise, which is where instead of what you might do in a traditional class where I give you definitions and then we start kind of doing math with them, our goal is for you to create the definitions yourself. Now, some of you, depending upon who you've had for previous teachers for your Intro to Proof class might have experienced some of these things we're going to do. If so, great. Don't go look it up. Don't go look up the answers. Instead, just kind of try to remember, but instead of trying to remember, try to think your way through, try to understand how these definitions come from and where they come from. Now, there's a real reason why I do this, and that's because I think that these few definitions that we're going to focus on are really the core ideas of the entire semester. And once these ideas make a lot of sense, then everything else, the really complicated stuff we do later, will all fit into this picture a lot better. So I want us to understand these definitions to the point that we could create them ourselves and then go forward to understand the rest of the semester, reading the textbook, doing the homework, and all of those things. So this first series studies sequences, and you're probably fairly familiar with sequences, but let's start by kind of talking about a definition. Now, a lot of books will have a definition that looks like this. A sequence is a function whose domain is the natural numbers. And this is different from most functions we're used to. Most functions, the domain is the real numbers. And so we get this nice smooth line graph or something that we deal with. But a sequence is the natural numbers. And what does that mean? It means the inputs are the numbers 1, 2, 3, 4, etc., etc. If you kind of aren't thinking about a sequence like that, if you're thinking about a sequence as just a series of numbers, then you're thinking correctly. So for example, the sequence 1, 2, 4, 8, 12. So if we keep going, I didn't have any pattern here. I was just kind of choosing some numbers. This is a sequence, and what you notice is that each of these can be identified with a real number. This is our first one. This is our second one. This is our third one. This is our fourth one. And this is our fifth one. So our sequences are just all of these numbers as we see them. And so what we might think is because, for example, because this is our fourth number, I would say A with a little 4 is equal to 8. So that 8, that little 4 tells us that it's the fourth number in the sequence. So when you see these subscripts and things, that's how we go. So this is the notation that we're going to use this semester. I actually kind of prefer some different notations, but we're going to use this because it's what's in the textbook, and it'll be just fine. Okay. So this is what a sequence is. We think of it as a collection of numbers, but there's another way to think of a sequence, and that is we could think of the sequence in terms of a graph. And so if we had a graph, what we would have is we would in fact only have the positive side of the graph because you can't have negative numbers come in. And so we'd have the number 1, 2, 3, 4, 5, 6, etc. And tell you what, let's just put 5 here, 10 here or something. And so notice that what we would do is we would just put a dot each time we see the spot. So at n equals 1, we have a dot right here. At 2, we have a dot at 2. At 3, we have a dot at 4. At 8, or at 4, we have a dot at 8, and then we have a dot at 12. So you can kind of see that our sequence, what we're doing is we're taking each possible point and we're associating a dot with it. And so it's tempting whenever I say draw some graphs, which I'll have you do in the near future, it's going to be tempting for you all to draw things that look like this. Technically speaking, that is not the graph of a sequence. This is a graph of a function that has real numbers as the inputs. So don't draw your graph like that. Instead, draw your graph with these dots, just as we're seeing right here. Okay, let's do a few examples, and hopefully these examples kind of bring to light what's going on. So here's our function, n, such that n is a natural number. That's how we should read this notation right here. It's saying n is an element of the natural numbers. By the way, it won't be very long until we remove that all together and we just write n for our sequence. Wow, those are some very poor curly brackets. Sorry about that. So it won't be long until we leave off the n. It's implied. But for right now, let's go ahead and leave it on there. So what is this sequence? Well, this sequence is just the numbers 1, 2, 3, 4, 5, etc. So it's just the numbers 1, 2, 3, 4, 5, on and on and on, and they keep going. If I were to think of this as a graph, this is a graph that's pretty familiar to you all. It's just a collection of dots moving in the positive direction. So 1 is 1, 2 is 2, 3 is 3, 4 is 4. Okay, hopefully this makes a little bit of sense. Let's move on to the next one, which is a little bit more interesting, and that is 1/2 to the n power. So what does 1/2 to the n power look like? Well, 1/2 to the n power, 1/2 to the first power is just 1/2. 1/2 to the second power is 1/4. 1/2 to the third power is 1/8, etc., etc. And so we can get all sorts of things here. And if I go draw my graph, what does this graph look like? Well, let's draw this graph. Let's make this 1 up here. And so we'll go 1, 2, 3, 4. And so at 1, our height is 1/2. At 2, our height is 1/4, then 1/8, 1/16. And what you see is that every time we're cutting that distance to the x-axis in half. So it's getting a little bit smaller every time we do this. Okay, you all might notice something interesting about this graph that's different between that one and the one we just did. This graph, the values keep getting larger and larger and larger, whereas this graph, they kind of consistently are approaching some number. They're approaching 0. And that's one of our first big challenges of the semester, to say, what does this approaching mean? What is this idea of a limit or convergence? What does this mean? Okay, and so that is that graph. Now, finally, I want to just point out something, and that is that you don't have to have an equation to have a sequence. So your sequences can be defined with equations, but for example, if I say let AN be a sequence that has the following values, that's actually perfectly fine. I don't have to have an equation attached to it. Sequence can be defined by a graph. It can be defined by relationships that aren't equation, but maybe recurrence relationships. So one that we might see later in the semester might look something like this. AN is 2AN minus 1 plus 1, and maybe we'll like take a square root of that or something. Okay, so this might be a relationship, and then if I tell you what A of 0 is, then you could get all the rest of the points by just putting them in this equation. Okay, so I didn't think too deeply about this equation. I don't think it's incredibly interesting, but there are some really interesting versions of this. That being said, I'm just saying this to point out that we don't have to have a beautiful equation in here in the AN part in order to have a sequence. These sequences can be messy, and they can be given just by graphs. Okay, the first thing I want to come to is I want to come to this idea of bounded. And so what does it mean for a sequence to be bounded? Well, let's come back and look at some of these sequences we've had in the past. And what you'll see is that this sequence right here, the 1/2 sequence, it makes complete sense to talk about this one being bounded. But whenever we talk about bounded, we always are talking about bounded by something. So we have to talk about what number it's bounded by. So for example, if I come over here and look at this one is clearly bounded above by 1. Okay, so that makes complete sense. It's bounded above by 1. But notice, it is not bounded above by, for example, 0.1. So if this was 0.1 here, it fails to be bounded above by 0.1 because we have several points that are bigger than 0.1. So I wouldn't say it's bounded above by that. And I feel like you all kind of have an intuitive feel for what bounded above should mean. Let's erase some of these things here so we can. Now, if I come over here and think about this function is very different. This function is not bounded above by anything, so it actually doesn't matter where I draw my line. I could draw my line way up here, but what do we know about the sequence? The sequence will pass it, and it won't be bounded above by that value. So any value you choose, this sequence is going to fail to be bounded above by it. Okay. Okay, so what's important is if we have bounded, first we probably need to say whether it's bounded above or below. We have those two options going on. And then we also need to kind of think about whether there's a number here that it's bounded by. Now, there is a general term for bounded, and we will talk about this in class on Monday. And that is that if it's bounded by anything, then we often will say it's a bounded function. So if it's bounded by 100, then it would be a bounded function. But like that first example, the n example, that one, there's never a number that bounds it. So that one would not be a bounded function. Okay, so that's something that we kind of talk about, but we'll get more into those definitions later. But what I want you all to do right now is I want you to create as many qualitatively different examples of functions bounded above by 10 as possible. And the way I want you to create these is I want you to use graphs to do this. So get yourself a piece of paper, draw yourself a bunch of graphs, and create a bunch that are bounded above by 10, and then a bunch that aren't bounded above by 10. And kind of try to think about what is the difference between the two groups. And then once you've thought a little bit about what the difference is, try to create a definition. And the a of n is bounded above by 10 if, and then say what condition is it that makes it to be bounded above. Hopefully this is not... hopefully this isn't too challenging, but I don't, even if you feel like you understand bounded, coming up with a good definition can be a challenge. There are some pieces there that are tricky. Okay, so again, do this with graphs. Don't feel like you have to come up with equations. Okay, the next idea that we're going to do is what's called eventually bounded. And just like bounded, when we say it's eventually bounded, we're going to need to talk about whether we're saying it's eventually bounded above or below, or both. Those are the types of things. And then we also need to have some number that we're talking about. So if I come back to this example we had earlier from this one was bounded above by 1. But what about this 0.1 value? Well, I would say it is not bounded I'd say it's not bounded above by 0.1, but I would say that it is eventually bounded above by 0.1. So what are we talking about when we talk about this eventually bounded piece? Well, again, this is part of what I want you to sort out, but I hope that it's a little intuitive. But you can see that our dots, the reason why this one wasn't bounded is because just a few of the initial starting point, right? So this first, second, and third dot threw it off. But if we kind of threw those dots out, then the rest of it would work. So you might say it's not bounded above by 0.1, but if I kind of use just this part of the graph, it is bounded above by 0.1. So that's what we're going to call eventually bounded above. Okay, so there we go. So I want you to think about this word eventually bounded above, and then for my second task, I want you to do the exact same thing you did for bounded, and that is create as many qualitatively different examples. Again, use graphs when you create those examples of functions eventually. Oh, I shouldn't say function. I should say sequence. Did I say functions on the last page too? I did. Okay, sorry. Sequences. Okay, so create as many qualitatively different examples of sequences eventually bounded above by 10 as possible, and then try to create this definition of what does it mean for a function, for a sequence to be eventually bounded above by 10. And as you can see, if you all get the words of sequence and function backwards, you should be able to say the distinction and say what's different about them. But they're also really similar enough that I wouldn't be surprised if you sometimes say the wrong word accidentally or even write the wrong word accidentally on your PowerPoint occasionally. Okay, so what do I want you to do for tomorrow? Or for class on Monday? For class on Monday, I want you to do both of these tasks and then record them in some way that you could share them with the rest of the class. So maybe that means taking photos of them with your taking a photo of your work with your camera so that you can share it over Zoom. Maybe you have an iPad or some device that you can write this on and easily share it. But think of a way that you can share these functions and share your definitions with the rest of the class. If you're one of the students who, due to time zones and other challenges, you're not going to be able to come to class, I would like you to take those examples that you created and send me your copy. So just you can take a picture of your work. You can, again, write it on an iPad, however you want to save your work and send it to me. And for this first one, you can just email it to me and we'll kind of work out what the best system is as we go through the semester. So thank you all, and I look forward to talking with you and seeing you all.